Performance and scalability go hand in hand, and many times it's hard to tell where one ends and another begins. In this section, we're going to be talking about both topics. Before we jump into an example of tweaking for resource utilization, let's talk about some things that we could do. One modification that we could make to the server for the API is adding on some kind of rate limiting. Right now, any user who's able to reach this API can hit it with as many requests per second as they feel like. Sometimes this is desirable, but in other times you want to limit the amount of requests that any given user can make per second so that all of the resources of the server are available for all of the other users. If you let any user get out of hand with the amount of resources they're using, that degrades the performance for everyone else. So when requests come into our API and we start processing them here, we could implement some kind of rate limiter that would keep track of how many requests this specific user, identified by IP address or token or whatever, has made in the last rolling 5 seconds or rolling minute, etc. And if they exceed a rate limit, we would send them back a "you've been rate limited" message automatically. And then once they have reached a rolling window where they have not exceeded the rate limits, we would allow them to make normal requests again. Since we would be implementing that here before getting our data store involved, that would save a lot of our backend resources. Or we could have a data store dedicated to storing the data we need to keep track of to know if any given user has exceeded their rate limit. Another thing that we could do when it comes to performance optimization should be fairly obvious. Right now, we are using the file system as a data store, and this simply doesn't scale, or at least it doesn't scale in a particularly elegant way. Right now, if any of our threads or any of our processes are trying to open files while some other process is trying to open that same file or write to that file, the results aren't going to be particularly nice. So this is obviously where a full-fledged data store comes in. A real database would allow you to make multiple simultaneous connections, send off your requests to read or write with various levels of consistency depending on your read needs, and internally that data store would queue your requests so that they're performed in an atomic fashion. Our file system isn't really doing any of that, and so this isn't the most elegant solution for scale. Also, since we are literally storing the data on a particular server when we're implementing a file system in this way, it doesn't allow you to scale your servers horizontally. Connecting to your file system from Node.js is fine, but you'd want the data store that it connects to live on some other machine that can scale with its own resources. And you'd want to be able to have your Node.js server scale horizontally without needing to keep track of which server has which data about which user. If you chose to implement a third-party database or a database of your own creation, you could have a data library much like this. You'd still want lib create, read, update, delete, and list. It's just that rather than having these functions read and write to the file system as they're doing here, you'd want them to directly connect to some other data store and perform the reads, writes, and updates and lists that way. Okay, so now let's move into a real-life example of how we could tweak for performance. Remember that tweaking for performance is really any kind of adjustments that you might make in order to save system resources under some situations. So the adjustment that we can make is actually to one of our handlers. If you remember back when we created the JSON handler for post checks, we have this taking in a bunch of inputs, looking up the user and the token that the user provided, reading in the user data, checking to make sure the user didn't have too many checks already, and then creating the check and writing it to the file system. What's going to happen after this, though, is that this check object is going to start getting checked regularly, which means if the user put in a URL that doesn't exist, or a URL that doesn't even have DNS entries, our workers, once this check is created, are going to start checking that same URL over and over and over again, even though there's really no reason to do that because it's never going to resolve. So one thing that we could do to optimize performance here is, rather than just blindly creating the check object with the URL that the user specifies, we can use Node.js to look up the DNS entries for this URL to make sure that that DNS exists before we allow the user to create a check with it. So let's go ahead and do that. In order to do this, we are going to actually use two Node.js modules, one that should be familiar and one that is brand new. So at the top, I'm going to add two new modules to our dependencies. One is URL, which we've used before for parsing URL data, and I'm going to call that underscore URL. And the other is DNS, which is require DNS. And DNS is the module that we're going to use to look up the DNS entries of the host name that is specified in the URL that the user provides. So let's go back down to checks post. Now, at this point, rather than creating the check ID as soon as we check that the user doesn't already have 5 checks, we first want to parse the URL to figure out the host name. We first want to verify that the URL given has DNS entries and therefore can resolve. The first thing that we need to do is parse the URL as we've done before. So we're going to use underscore URL.parse. We're going to add on the protocol that the user specified, and then append : / then add on the URL that they specified and say true. I'm going to call this parsed URL. Now we need to grab the host name out of this parsed URL. So we're going to say var hostname equals type of parsed URL hostname equals string, and the length is greater than 0. But we'll default it to false. So now we want to use the DNS module to try to resolve this host, which is basically going to try to check for the type of DNS records that we would need before we could ever make an HTTP request to this URL. So we're going to call DNS resolve, pass in the host name, and then expect back an error and DNS records. At this point, if there's no error and there are records, then we can continue on with the rest of the logic here. Otherwise, we're going to send an error back to the user. That's a 400, and an object saying error. The host name of the URL entered did not resolve to any DNS entries. But if everything's fine, I'm going to take everything that used to happen below here, and I'm going to paste it inside. Now, one thing to note, whether or not the DNS resolves successfully will depend on your ISP. In my experience, some ISPs take it upon themselves to resolve all non-resolvable addresses to one of their own pages. And this is generally so when people enter a misspelled URL in the browser, that ISP can serve them with some kind of ad. So it's possible that when you try to resolve unresolvable DNS here, you still get some kind of results, and there isn't much that you can do about it, except for try to host your site on a machine inside of an ISP that doesn't do that kind of thing. So let's start this server back up and try to see what happens. Okay, first I'm going to post to the token service with the credentials of the user that we've been using recently. And now I have a new token that I can use in subsequent requests. So I'm going to do a post to the check service, but I am going to update the token here. So I'm going to send a post with google.com to API/checks. I got a 200 back. Now I'm going to try to send a URL that shouldn't exist. I'm going to create this long URL that no one should have ever registered. Send that off. and we get a 400 back. The host name of the URL entered did not resolve to any DNS entries. Again, this might be the results that you experience on your local host. It really depends on your ISP. If you're on a good ISP, then this is the result that you'll get back. Okay? So, how does this help us with performance? How does looking up the DNS help us with performance? Well, imagine that out of all of our users, 1% of the checks that they create are accidentally to some URL that doesn't exist or doesn't even have DNS entries. Well, then our workers, once a minute, are using up system resources to perform checks over and over and over again to DNS that will never resolve. That's going to use up resources for no reason. And so implementing this kind of thing ahead of time, upstream of that problem, should help us alleviate the majority of those situations. It's also a benefit to the user where we are catching errors that they might not have noticed that they put in the first place. Okay, so we've talked about a bunch in this lecture. We talked about refactoring our data library to use external data stores. We talked about implementing a rate limiter, and now we just did an example of modifying one of our API routes to save system resources downstream of that route. Now that we have that in place, we can move on to the next lecture, where we're going to talk about the performance hooks module and how you can time the execution of some of your code.